In this lecture, we look at the slope of a function or function linearization. We're going to approximate a slope near a point by a line. Linear functions are the easiest function to understand, and for this reason, we often seek to replace a more complicated function f of x near a point P by a straight line, that is, by a linear function of the form Lx equals mx plus b, where this linear function L of x looks an awful lot like f of x near this point. If we know the slope of the function at P, this is easy to do. We simply write out the equation for the line through P with that slope using the point slope form. For example, suppose we have the function f of x equals square root of x, definitely not a linear function, going through the point 4, 2. You might verify that when we plug 4 into this function, we do get out 2. And suppose someone told us that at that point on the curve, my function has slope 1/8. Let's find the linearization of this square root function at 4, 2, and let's use our linearization to estimate the square root of 5. Now we've been given that the square root function goes through 4, 2 and has slope 1/8. We want to find the linearization there. Well, from an earlier problem we did in an earlier lecture, we found the tangent line at P using the point slope formula to be this. We discovered that if x is 4 and y is 2 and the slope is 1/8, that gives us the line y equals 2 plus 1/8 times x minus 4. So there's my linear function. This function looks an awful lot like the square root function near 4, 2. Now, if we need to approximate the square root of 5 using this function, then notice that we already have this equation, the linearization for the function, a line that looks like it. Now, in the square root function, to get the square root of 5, we plug in x equals 5. So let's take this linearization and plug in x equals 5. We're going to plug in x equals 5. Instead of plugging it into the square root function, we're going to plug it into this one. So if we plug in 5, we will get an answer of 2 plus 1/8 times 5 minus 4, which is 2 plus 1/8, which is 2.125. To stress, instead of plugging 5 into the square root function, we plug 5 into L of x because they're very similar. Here's another type of question along the same lines. Suppose we have the graph of a function that goes through the point 2 minus 1, and suppose near that point the graph looks very much like a line with slope 4. Even if the function is not a line, what can we do with this? Can we do things like find out where the function hits the x-axis? Yes, we can. We can replace the function by the line that looks like it. We're told that the function looks like a line of slope 4 through 2 minus 1, so let's use the point slope formula. The slope is 4, which is rise over run, or y minus 1 over x minus 2, which is the same as y plus 1 over x minus 2. And so if you want the x-intercept, then I need to find out where y is 0. So if m is 4 and y is 0, then 4 is 1 over x minus 2. That implies that x minus 2 is a fourth, which implies that x equals 2 plus a fourth, or 2.25. This is a good first approximation for a 0 of the function f of x, even if the function f of x is not really a line. Observe that in each of these problems, we get some original information from the function, the slope of the point, and then we ignore the more complicated function and use a simple line instead. The concept of function slope or function linearization is a powerful idea. We will explore it throughout the course, but here's a quick glance at some of the applications. How might one compute the cube root of 9? Of course, we now have calculators to do this, but how do our calculators make these computations? I'm going to provide a rough answer to this question by using linearization in two different ways. In both cases, I will magically provide the slope of a function at a point, and I hope that this magic is impressive and worth learning. You will see as we go that it's very important that we know what the slope of the function is. All right, we're trying to find out about the cube root function, and it goes through the point 8, 2, since the cube root of 8 is 2. It so happens at that point, magically, take my word for this, that the slope is 1/12. Let's linearize the function there at the point 8, 2. So by the point slope formula, y minus 2 is 1/12 times x minus 8, or better yet, solving for y is 2 plus a 12th, x minus 8. So this new function, the linearization function, in this form, approximates the cube root function near the point 8, 2. So instead of evaluating the cube root at 9 by plugging in x equals 9 into the cube root function, we're going to evaluate the cube root at 9 by approximating it with this linear function. Let's plug 9 into this linear function. If we do, we get 2 plus 1/12 times 9 minus 8, or 2 plus 1/12, or 25/12. This linear function tells us that when you plug 9 into it, you get 25/12. So when you plug 9 into the cube root function, you must get something close to that. The point 25/12, or 2.083 with the 3 repeating, is a good first approximation for the cube root of 9. It's accurate to at least 2 decimal places. Cube root of 9 is about 2.08083. The zero, one more problem. Let's find the zero of this function. The zero of the function x cubed minus 9 is cube root of 9, so we're getting ready to estimate cube root of 9 in a different way. We're going to look at this function, g of x, which is not a line, and find a nice linearization at some point on the graph where the graph is close to the x-axis, because I'm really trying to figure out where y is 0. We're going to use that linearization to guess the value of our 0. Now the point 2 minus 1 is on this curve, and so it's a good choice for a nice point close to the y-axis. So let's linearize my function g of x at the point 2 minus 1. And it so happens, take my word for it at the moment, that the slope of the curve there is 12. So this messy function x cubed minus 9 at the point 2 minus 1 has slope 12, so we're going to use the line with those properties to approximate this more complicated function. The linearization of g of x at this point is y plus 1 is 12x minus 2, according to the point slope formula. And so we have this line, I'll call it L2. L2 of x is minus 1 plus 12 times x minus 2. Instead of using x cubed minus 9, as my function, I'm going to use minus 1 plus 12 times x minus 2. And instead of asking where is g of x 0, I'm going to ask where is L2 of x 0. So for my linear function, I make the y value be 0. I'm going to solve 0 equals minus 1 plus 12 times x minus 2. That gives me this. And after I solve it, I get x is 2 1/12, or 25/12. This again gives me a nice approximation for the cube root of 9. If we take just a moment, this second method, I tried to find a 0 or a particular function and got 25/12 or 2 1/12. So once again, I'm sort of verifying that the cube root of 9 should be close to 2 1/12. It's been a little time going through these two examples. This concept of function slope is a critical one. We will use it all semester. In the next few lectures, we will describe the average rate of change and the instantaneous rate of change. The instantaneous rate of change is the same as the slope of a function, and we will use the ARC to compute it.